today. I want to start by just very quickly reviewing Bayes' formula, and especially I want you to be able to derive it with your eyes shut and your hands behind your back. So you start with the joint probability of the parameters in the data, and you break them down by the chain rule two possible ways. Either P of theta times P of D given theta, or P of data times P of theta given data. And then you identify the posterior, because Bayes' formula is all about deriving the posterior from everything else. And the posterior is the probability of the parameters after you saw the data. Probability from after you saw the data, you just isolate this part, so it's this times this divided by this. P theta times P data given theta divided by theta. I'll just write it in a slightly different way. Statisticians like to use pi for prior and L for likelihood. And this is just the evidence, P of D, which can also be written as an integral over the exact same expression as you have here, except with a prime here to say it's a dummy parameter. This is L of D given theta, D theta prime. And now the other thing we did was we defined H map or theta map, maximum posteriori, is defined as the argmax over all possible thetas of the posterior P of theta given D, which can be written as argmax over all possible thetas of this thing. But in this thing, P of D is a constant with regard to what we're maximizing over. It does not depend on theta, so it ends up being just dependent on this product. P of theta times P of data given theta. You don't need to copy all of this because you have it already, but if it helps you remember it, write it down. So something that any well-educated person should know. We went further and discussed the case where P of theta is uniform, the prior is uniform, in which case it's constant, it does not depend on theta, and the maximization depends only on this. In that case we have theta maximum likelihood. So you can always define the maximum likelihood theta, maximum likelihood solution, but when the prior is uniform, it is the same as the map solution. In the general case, the maximum likelihood solution is argmax over theta of just P of data given theta. There is sometimes confusion about what maximum likelihood means. Since the likelihood is a function of the data, conditioned on the parameters, sometimes you might be tempted to think, well, we're trying to find the highest points of the likelihood, what data is most likely. But it's not the case. Whenever you apply the maximum likelihood principle, the data is fixed. And really what you're asking yourself is what value of the parameters would give it the highest possible numerical value. And you achieve that by taking the derivative of the likelihood function with regard to the parameters theta. Remember, theta could be one or more parameters, and just setting it to 0 and making sure you get the maximum, not the minimum. We did this for the case of flipping coins, and we discovered, not surprisingly, that the maximum likelihood solution is the relative frequency count, number of heads divided by total number of tosses. The common intuition that every high school kid has, we found that that's the maximum likelihood answer. Which means it may or may not be the map answer. If the prior is not uniform, it is not the map answer. I also ask you to do it for the case of estimating the mean of a Gaussian from a set of points generated by the Gaussian. And it's in your homework, I guess. It may not be done yet. But the answer there is also not very surprising. I want to show you some other cases where applying the maximum likelihood principle results in interesting answers. So, here's a case. Suppose you're trying to learn a real valued function. The data, I'm copying it from your slide, so it's on the slide somewhere. Data looks like this. And you don't assume that there is a function deterministically goes through all these points. You could. These points, as you see, don't look at a straight. They're not on a straight line, and you will need to have a fancy function to hit them exactly. What you might want to do instead is assume that the data comes from a simpler underlying function, maybe a straight line, but that there's added noise to it. And the noise could be in the x-axis or the y-axis. Let's assume here the noise is in the y-axis. So there is some kind of a simple function, maybe a straight line, and that function is given by y equals f of x, or yi equals f of xi. And f is presumably a simple function. But then the actual data points, call it di, is given by f of xi plus some noise, which in the book is called pi. Plus some level of noise. And notice that the noise could have been here too. So you choose an x, you come to the point of f of x, and then you apply a noise in the y dimension. But you could have applied one in this dimension too. But for the case that we're analyzing, there's noise in the y dimension. The point moved up or down. That noise is assumed to be Gaussian with mean of 0. Why are we making that assumption? Because in the real world, noise often behaves that way. If the noise consists of is created by many contributions of many different things that are not correlated with each other, the central limit theorem says that, and as the number of such components grows, the total contribution of the noise will tend to be Gaussian, and if it's unbiased noise, it'll be centered on 0. So we will assume that your y comes from some Gaussian with mean 0 and some standard deviation. Now we're looking for the maximum likelihood solution, and the solution is over the set of all possible functions f. So the hypotheses are all possible f's, and let's say you have some set of h's, some hypothesis space h, and you're trying to find the one h that has the highest likelihood of generating this data. So what do we mean by likelihood of generating the data? In this particular case, the xi's are given from the outside. They're not part of your generation process. Maybe they're generated by some process, but you're not trying to model that. What you're trying to model is, for any given set of xi's, what are the di's that come out? So the data consists of x1 d1 xn dn, but you're really not we're not defining the likelihood to include generating the excess, but only generating the d's given the excess. This is called conditional likelihood, but it's likelihood nonetheless. So we'll write the expression for the likelihood, or I'll call it explicitly conditional likelihood, That would be L of D given our hypothesis H. And the first thing to notice is that the different data points are generated independently of each other. Let me just write that explicitly. This is L of the DI, D1 through Dn, given the hypothesis H and the Xi through Xn. So I'll erase it from... I don't want to confuse you since I wrote D here, and D consists of everything. That is, this is the full likelihood, and I'm looking for the conditional likelihood. This is the conditional likelihood. Nonetheless, we know that DI depends only on Xi and H. So we can write it as a product of the probability of DI given Xi and H. It goes from 1 to n. Now I want to find the maximum likelihood. So the maximum likelihood hypothesis would be the one that maximizes over all possible H's in the hypothesis space the product P of DI given H and Xi. Max. Now, if we're given an H, that determines our f, our function f, right? H is the function f. It's a set of all functions that we're considering. So it determines a particular function f, and we have the x. So this gives us deterministically where we are on the line. Have some xi here, will be here. The only thing that's not given is how much noise are we going to have, up or down. That's given by the Gaussian. What is the probability of the Gaussian generating the particular DI point? Well, that depends on the distance of the DI from the line. So that would be product of the Gaussian form, 2 pi sigma times e to the negative half DI minus h of xi squared divided by sigma. I like to put 2 sigma at the bottom, but okay? This is just writing this here. The xi found its way here. The h or f, same thing, found its way here. The di is here. And the distance of the point from where the deterministic function would put it is governed by a Gaussian, which is why we have this expression. From here on, the rest is algebra. First, I'm going to argue that the h that maximizes this first of all, I can cross this out. It's a constant with regard to the h. It doesn't change. Second, the h that maximizes this also maximizes its log. And effectively maximizing the log of the likelihood rather than the likelihood. So that would be the same as argmax over all possible h's that are allowed of a log of this would be the sum of the log of this. Right? And the log of this would be just getting rid of the e. So it'll be minus di minus h of xi squared, and this time I'll put it at the bottom, 2 sigma at the bottom. Sigma squared. Thank you. Okay, but regardless of whether it's sigma or sigma squared, it's a constant with regard to h. So we can cross that out too. I'd like to cross out the negative also, but to doing that I need to change the max into a min. So this would be argmin h of sum of di minus h of xi squared over my training data. So what did I get? I got that for any time I'm trying to model a function, I'm trying to find a function, and I have reason to think that the output of the function is somehow corrupt or changed by a Gaussian noise. Okay, that's the only condition I'm in. There's some function, some deterministic function plus Gaussian noise. So whenever I'm in that situation, the maximum likelihood solution is a solution that minimizes the sum of squared errors. That's a very fundamental connection. Remember we talked about different error functions when we dealt with neural networks, for example. Our favorite error function was the sum of squared errors. We had a big 1/2 in front of it to help us with the derivation, so it would cancel out. But essentially it was a sum of squared errors. And I mentioned at the time that there are many reasons for doing that. One is that the calculus is really easy because you take the derivative and you end up with a linear formula. But there's a much deeper reason. And the deeper reason is that the sum of squared error criterion, if you're trying to minimize the error, you're trying to minimize the sum of squared error, minimizing that corresponds to trying to maximize the likelihood of the data under the assumption of Gaussian noise. So the take-home message is, Gaussian noise minimize mean squared error. I'm writing here mean squared error, but mean squared error and the sum of squared errors are kind of the same thing, right? It's whether you divide it by n or not. There are other setups under which the minimizing the square errors would not be the right thing to do. For example, suppose what you're trying to learn is not just a numerical function, but the probability of a certain event occurring under some conditions. Statisticians have names for these kind of setups. The setups I described for you now, we're trying to find a function that matches with Gaussian noise is part of regression or linear regression. Generally trying to match the value of a function given its input. The input could be one-dimensional or 100-dimensional or anything. Trying to predict what the value would be and minimize your error is called regression. When you're trying to predict not a value of a function but the probability of an event occurring, that's called logistic regression. The difference is that in regression the training data looks like what you're trying to predict. The training data consists of x1 d1, x2 d2, x3 d3, and therefore you're given x5 and you ask what would d5 be. And you're measured by how accurately you can predict that. In logistic regression, you're given x1 and then whether the event happened or not. Let's say 1, it did. x2 and then the event happened or not. Let's say it didn't occur. And then x1 again, and then this time the event didn't occur. And then x1 again, and this time the event occurred. So actually it's not a deterministic function. The data that you're given does not come from a deterministic function. It gives you certain conditions characterized by the x, and then it tells you whether the event happened or not. And now at test time you're given x1 and you're asked not to predict 1 or 0 but to actually give a probability the event happened. Probability of 1 given x1. And the same for all the other x's. So you're trying to estimate the probability of an event happening based on maybe how many times it happened in the training data. And of course the trick is that some of these events will happen very few times in the training data, maybe once and maybe even 0 times. Just like in a regular regression, you're only given a few data points and you're asked to predict what is the value of this data point that's not here and not there. You're doing some kind of interpolation. Well, you might do the same thing with logistic regression. So if it's logistic regression in one dimension, let's say this is x, there's just one x, and this is the probability of one given x, namely the probability of the event occurring given that you have x. The function might be, so this is bound between 0 and 1. The function might be anything, but you could assume maybe that it's smooth, it doesn't change too fast, so maybe it's something like this. Now, how are you going to learn whether it's this function or something else? Remember that the only data you have is not the value of this function. You have only occurrences. So whenever x was here, you saw maybe one positive example and 5 negative examples. 5 examples where it was 0, when the event didn't occur. When x was here, you saw, for this one, you saw some positive examples and maybe a few negative examples. And for many of these you didn't see, and you're trying to fit some kind of a curve through it. So you may need to make other assumptions too, but what I'm trying to impress upon you is that the setup is very different. You're not given explicit examples of what the output should be. What you're given is outcomes of events, and from this you have to go back and deduce what the probability of these events are. The reason I'm telling you all of that is that when you're in that setup, the minimum squared error is not the right measure. The right measure turns out to be cross entropy. But to derive that, you go back to the more fundamental principle of maximum likelihood. So you write down the likelihood function, and you go through the same process we went through here. You say what values, when does it achieve its maximum? And maybe you have to take a derivative or something. And the answer you come up with guides you to what error function to use. And people do that all the time in neural networks. So when you use a neural network to predict probability of events, the error function you should use is not squared error. It's cross entropy. And then you start with that as your error function, and then you have to derive your gradient descent from it. Because remember that gradient descent is done relative to some error function. So you decide on the error function, and from that you take the derivative and you derive your step change, your weight change rule. But it all can be traced to maximum likelihood. I don't mean to say that all of statistics or all of what we do traces to maximum likelihood, but everything we discussed here, if you start from maximum likelihood and work your way backwards, you say my principle of estimating is the maximum likelihood, okay, what error function does it imply? And then you take the error function and derive the learning rule from it. Questions? In the slides and in the book you have the actual derivation of the case of cross entropy because of logistic regression. Okay, maximum likelihood is not a Bayesian concept. Bayesians don't like maximum likelihood. But it's still a very useful concept. But let's go back to Bayesian thinking. And in Bayesian thinking we deal with posteriors. What we really care about is the entire posterior function. Now if we only half-heartedly Bayesians, we take our posterior function and just grab the maximum of it, or the mean, or the mode. But most likely the maximum. That's the map. Let's do it for now, and then we'll go and become even more Bayesian and refuse to do that. But for now, let's concentrate on HMAP. So we're here. Imagine that you have a large amount of data that you're trying to training data that you're trying to communicate to a friend over a slow channel. So it's important to be efficient. This notion of important to be efficient may seem contrived to you, but actually it's a very useful way of thinking about how to generate regularities and how to get to the essence of things. If you remember in neural networks we said that when you have a bottleneck in the network and you're forced to go through the bottleneck, the network must, in order to do it properly, if it can do it, it must find a solution that captures the essence of the data and sort of gets rid of the idiosyncrasies. So it's very useful to think in terms of what happens if you need to compress data, pass it through a bottleneck. So suppose you have a large amount of data that is that you're trying to communicate to a friend who's far away, and it costs you a lot of money for every bit, so you're trying to minimize the cost. Now the data is given as, say, x's and y's, x1 through x million, and here is y1 through y million. Now your friend already has the axis. And they're even sorted in the right order, perhaps. In the same order, so you both have a ranked list of x's. And they don't have the y's. This is what you're trying to send back to them. So the simplest thing is to send them the, let's say the y's are binary. So y is, say, 0, 1, 1, 0, 1, 1, and so forth. The simplest thing to do is to just send them the long list of bits. Right? That's a million bits. You could pass it through some compression scheme that would make it less, maybe, if it's compressible. But suppose that the way the x's were used to derive the y's is quite regular. That there is a real function, real underlying simple function out there. Maybe that function could be expressed by a simple decision tree that has only 5 nodes. In that case, you might be better off just sending the decision tree over and telling your friend, just take all of the x's and pass them through the decision tree, and whatever outcome comes out, that's the right y. So it's a useful way to think about how much information is really in the y's, given the x, given that you have the x's. An upper bound is just a string of all the y's. But if the y's were generated from some underlying simple function, just send the function over. Well, what if there is no simple decision tree that explains all the data, but there's a simple decision tree that explains 99% of the data? Well, what could you do then, if what you care about is minimizing the number of bits you send your friend? Please?
Send the right ones. Give them the decision tree, and then send the bits for the wrong ones.
Right. First send the general rule, and then follow up with a list of exceptions. Since the output is binary, all you have to do is identify which are the exceptions. Right? If something is an exception, that means if the decision tree gave you a 1, turn it into a 0. If it gave you a 0, turn it into a 1. How much does it cost to send the exceptions? Well, since you have the ordered list, you just need to send the index of the position that has the exception. Let's say this is an exception and this is an exception. This x37 and x500 or whatever. And the index of a million possible outcomes is just log base 2 of that. So you just need to send about 10 bits for each one of them. Now, you came up with a 5-node tree that had 37 exceptions. A different person came up with a 7-node tree that had only 2 exceptions. And yet another person came up with a 10-node tree that has no exceptions. Which one is better? They can all be used to send the data, right? You send the rule, then you send the exceptions. But there's a trade-off here between how simple the rule is and how many exceptions there are to it. Which one would you choose? Then? It depends on how you encode the tree. Is that right? Can somebody explain what that meant by this? Did you have to get up extra early today to vote?
Yeah, it would mean the number of bits required to encode each node of a tree, and also the number of bits required to encode each exception. So the total should be less, depending on that.
Okay, so you have to count how many bits it takes you to encode each tree, and that's usually proportional to the number of nodes in a tree. Right? And then you count how many bits it takes you to encode exceptions, and you just add those bits up. Right? Because that's our goal, minimizing the number of bits. So we can call this the principle of minimum description length. Or MDL. And we can use it as our criterion for choosing a hypothesis. So we'll call it H sub MDL. It's defined as, hopefully you can derive the notation with me. You already know HMAP and HML. Now we have HMDL. It'll all start the same. Some arg max, or in this case will be arg min. That one hypothesis among all the hypotheses that we consider, all the hypotheses in the hypothesis space, that minimizes the total number of bits needed to transmit the training data. And that total number of bits consists of two components. The number of bits required to transmit the rule, plus the number of bits required to transmit the exceptions to the rule. So this would be I'll use the notation from the book. It's just LC1 of H stands for length of the coding of H plus LC2 of the data given H. Again, the data we're talking about here is very similar to the example I gave you before. It's the y's given the x's. The x's are assumed to be given. So it's conditional data. LC stands for length of coding, and it's measured in number of bits. Now, how many bits does it take to encode a tree of 7 nodes? Well, it depends on how you agree with your friend you're going to encode trees. You had to agree in advance that what you're going to send them would be a decision tree. And you had to agree in advance on the convention for how to encode it. And there would probably be some fixed part which says how many nodes there are. Maybe some other, there's y to yes to the left and no to the right, or whatever. There may be some idiosyncratic things. But for the most part, the number of bits needed is linear with the number of nodes. And the number of bits needed for each node will depend actually on how many attributes you have. It's the log number of attributes, because you have to specify the attribute. And if the question there is not only the binary attribute, but if it's something like is the temperature greater than 50 or less than 50, then you may need some more information to encode a number. So there's some details that have to do with the decision tree. And of course, you didn't have to choose a decision tree. You could have chosen a neural network, or you could have chosen anything else. But you have to agree on a scheme, and then to agree on a representation scheme, on the way of using bits to represent the particular choice of parameters. Number of nodes, topography, weights, and so forth. But, so arguably there's a certain amount of arbitrariness in how many bits it takes to encode things. It depends on your encoding. But all reasonably efficient encodings of things like decision tree would agree asymptotically. In the sense they would all be linear in the number of nodes. Okay, I cannot imagine an encoding of a decision tree that is logarithmic in the number of nodes, although who knows. My belief is that you have to have at least linear, and if somebody came up with an encoding that was quadratic in the number of nodes, I would say that's not efficient, let's use something else. So if those of you who've taken computability theory and complexity theory will recognize this notion of encoding is somewhat arbitrary, but asymptotically it's generally accepted to be, at least all reasonable encodings are related to each other polynomially. So this is for the encoding of this part. Somewhat arbitrary, but arbitrary up to some constant, let's say. This part, in our case, was extremely simple. You only had to specify the exceptions, and the rest is clear. but it can be generalized to real-valued functions. So here we have binary functions. But the way you would generalize it to real-valued function is as following. Suppose you're trying to learn a real-valued function, and the points that you have look something like this. Okay? Now you think this comes from a second-degree polynomial, a parabola, but actually it's almost, but not exactly right. It looks like this. It misses it by a little bit. This is the closest parabola you can fit, a mean squared error fit of the parabola. Okay? Now if you really want to hit these points, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 points, you can have an 11th degree polynomial that would hit them exactly. Polynomial would look something like this. I think we've gone through this before, haven't we? We don't believe that it's really an 11th degree polynomial that generated it. But what about a third degree polynomial instead of a second degree polynomial? The third degree polynomial would be very similar to the second degree one because it has one more coefficient. It could come a little closer. And in fact, the mean squared error, the total squared error, is guaranteed to be a little bit better than in the case of a second degree polynomial. So the third degree polynomial might look like, I don't know, something like this. So in fact, we have a choice between a first degree polynomial, second degree polynomial, third degree, fourth, all the way to 11th. There's no point in going beyond 11th because at that point the error is 0. When we talked about Occam's razor, we said that we would, one of the fundamental choices in modeling is balancing the simplicity of the explanation with the goodness of the fit. Right? This is what's going on here. Now you can also use this in the framework of transmitting bits. And the way you do it is first you transmit not a decision tree but a polynomial. You have to first say the degree of the polynomial and then transmit the coefficients of the polynomial. So again, the number of bits used are proportional to the number of coefficients, namely to the degree of the polynomial. Very much like the number of nodes in a tree. Now, how many bits do you need to specify each coefficient? Now it gets tricky because how do you specify a real number with a finite number of bits? So you have to make some changes. You have to talk about approximations. But let's say you restrict yourself to coefficients that have only 10 digits or 10 binary digits or 100 digits and some fixed number. So this is okay for this part. This could be a decision tree, a neural network, or a polynomial. The second part is how do you transmit the what we call the exceptions before. Here it's not exceptions, the error, the remaining error. Well, now it gets a little trickier. Suppose you're using the first degree polynomial and you have a substantial error here. You would like to define the number of bits such that it gets worse and worse as the error gets larger and larger, right? So there's a certain amount of arbitrariness there too. But suppose you knew that the error came from a Gaussian. And that would put some kind of distribution here. I'll put it sideways. Not very good. This is the point that your function predicted, and this is how far you got. You can assume with your friend that you can pretend with your friend that there's a Gaussian that generated the noise. You don't have to assume a Gaussian, you can assume something else. But if you agree with your friend that the discrepancy between the simple rule you sent them and the actual value comes from an additive Gaussian noise, let them pretend that it came from a Gaussian noise, then you can measure the degree of deviation, or the error, by the value of the Gaussian on this distance. So I just argued that you could use the MDL principle even for functions that are real valued functions, although at the end it got a little fuzzy, like how do you define exactly the number of bits needed to transmit the error. Let's leave that and go back to map. Here's our definition of map from Bayes' concept. And let's manipulate it a little bit. I have here argmax theta of this product of the prior and the likelihood. And I'm going to do my usual trick and say that this gets its maximum. Theta that gives the maximum is also the one that gives the maximum to the log of this. So I'm going to stick a log inside here. And if I put a log, this becomes a sum. So it's a max of log P of theta plus log P of data given theta, the likelihood. So the map principle says I should find the theta that maximizes the sum of the log of the prior and the log of the likelihood. And now I'm going to introduce a negative sign here and convert it from max to min. So arg min over theta of negative log P theta minus log P of data given theta. So this is still map, the definition of map. And now I'm going to take you back to information theory and remind you that in information theory we measure entropy as the average negative log likelihood, and we said that one definition of entropy, one way to understand entropy, is the minimum number of bits required to transmit messages from that source. It's a lower bound of number of bits, and in fact the lower bound is achieved, so there is a code for any distribution, there is a code that is as efficient as its entropy. And when you use that maximally efficient code, every message is encoded with a number of bits that is a negative log of its probability. So you can think of negative log probability as a number of bits required to transmit a message under most efficient coding. So we can now think about this as number of bits required to transmit the prior, the value of the prior, the value of the parameter based on the prior, which corresponds to the number of bits required to transmit our hypothesis. H and theta are the same thing. Whereas the number of bits required to transmit the data given the value of the parameter, or given the hypothesis, is this part. So it's really one and the same. MDL principle was invented by computer scientists who perhaps should have studied their statistics better, because it existed effectively in statistics as map before. Now, I'm being a little facetious here. There's a lot more to it, because in computer science you care very much about encoding, and the issue of how you encode and what you encode, and number of bits and so forth, is not something that statisticians typically, at least until then, dealt with. But nonetheless, mathematically, MDL and map are the same thing. And how you choose to encode, how do you allocate your bits for the hypothesis, effectively determines your prior. A Bayesian would come and look at it and say, aha, when you choose the number of bits here, you're effectively choosing a prior, even if you don't admit it. And how do you decide how many bits to assign to describing the discrepancy is effectively determining what? The likelihood function. This L should have given you a clue. This is the prior, this is the likelihood. Questions or comments? Okay. I want to make sure that I finish all this material, so I'm going to take a deep breath and use the slides. We followed the progression here. In the beginning of the class, we worked with maximum likelihood, which is the most non-Bayesian thing you can do. It doesn't consider a prior, it just looks at the likelihood. Then we moved back to map, which is sort of a halfway point. You do consider the prior, but you only consider it in order to generate a posterior. Once you generate a posterior, you take the maximum of that posterior and you run with it. That's not what the true Bayesians do. The true Bayesians don't run with one maximum of the posterior. They try to keep around the entire posterior and use it. Why is that useful? Sometimes they have a point. And the reason it's useful is the following scenario. Okay. So if you have to choose one hypothesis, you could argue you should choose map, the one that has the highest posterior. But very often you don't have to choose one hypothesis, you just have to classify new instances. Okay? If you were going to the desert and you could not afford, or to a desert island, and you could not afford to take the whole posterior with you, you could only take one member of that posterior, one function, then take the map function. But if you're not going to a desert island, if you stay at home and you can afford to keep the entire posterior around, keep it around and consult the entire posterior when you try to classify new instances. Why is that better? Imagine that you have three possible hypotheses, H1, H2, and H3. And these are their posteriors. After you saw the data, the posterior assigns that 40% that H1 is correct, 30% that H2 is correct, and 30% that H3 is correct. So if you were to choose the most likely hypothesis by its posterior, you would choose H1. This is the map hypothesis. But suppose now you're given a new instance, X, and you find that H1 classifies it as positive, H2 and H3 both classify it as negative. How would you classify it? Which is the most likely classification? Which classification is optimal given your worldview? Well, the answer is that even though if you had to choose one of these three, you'll choose H1, if you have to choose a classification, you're better off choosing the negative classification, the minus. Because both H2 and H3 agree on it, and combined they have a total posterior of 60%. Okay? Two different things. One is if you were judged by do you have the correct hypothesis in your hand, then you should choose H1, and you'll be 40% chance of being correct. But if you're not judged by whether you have the right explanation in your hand, you're only judged by your prediction, then you should choose minus, and you'll have a 60% chance of predicting correctly in this particular case. So you're better off hedging your bets and waiting and keeping all the hypotheses around, and when you have to make a prediction, consulting all these hypotheses. You know, it's a little bit like these elections. You could, for every question you have, ask everybody, right? That's a referendum. Or you could choose one person a priori that you think is most likely to have the right answers on average, and let him answer all the questions. I'm not advocating changing the political system, but it is very similar in the sense that do you commit to a person, to a decision maker, to a hypothesis, or do you not commit, keep things flexible and make a decision on the spot? So from a Bayes point of view, you should always not commit. You should always take a vote. The only difference from a democracy is in democracy presumably you take a vote where each person has one vote. Whereas in the Bayes world you take a vote but it's a weighted vote, weighted by the strength of the posterior. So maybe a better analogy would be a bunch of experts that you brought into the room, and you have 100 doctors to discuss a difficult medical case, and you can either choose the wisest doctor or the doctor that you think is, agrees, predicted the best so far, and then ask them all the questions and let them make the decision, or you can every question pose to all the doctors and weigh their answers by how wise or relevant they think they are. The Bayes way is always the second way. Only one problem with that. Can you guess what it is? What could be the problem with voting all the time?
It takes too long.
It takes too long. Yeah, computation. So if you have 3 hypotheses, it's not a problem. What if you have 3 billion hypotheses? Or what if you have a continuous number of hypotheses? You have to integrate over them. So that's what Bayesians do all day. They integrate all day long. If you see a lot of integrations, and I'm Bayesian, I'm just making fun of myself here, but if you see a lot of integral signs in a statistics paper, chances are somebody is integrating over the posterior. And a lot of work has gone into how to do integration efficiently. If you can do it analytically, of course, it's great. Usually you can't, so you need to approximate it. You can sample it. There's a huge amount of work on that. And there are many times when correct Bayesian solutions are known, but nobody's found an efficient way of using them, so they're not used. On the positive side, a Bayes classifier, a Bayes optimal classifier, is guaranteed to have the lowest possible average error. Under what conditions, can you guess? When is it guaranteed to have the lowest possible average error? When you have the right prior and the right form of the likelihood function. Remember the small little details. So the definition of a Bayes optimal classifier, if you have V labels, not just 2 but any number of labels, and J is the index over the labels, it's the classifier that assigns the label that maximizes the vote. And what is this vote? You start by figuring out how much weight a particular hypothesis should have, and the answer is it should have as much weight as the posterior gives it. So this is the posterior for hypothesis HI. And that particular hypothesis might not vote only for one label. It might actually vote for multiple labels. In the cases we considered until now, like the plus and minus, each hypothesis voted fully for plus or minus. But in the general case, each hypothesis might vote for each one of the labels, with some probabilities that of course have to sum to 1. So it's like you're posing a medical question to a room full of 100 experts, and there are 3 possible things you could do. You can do this surgery, or no surgery at all. And you ask each doctor to give you a weighing, from 1 to 100 of 30% do this and 40% do that and whatever do that. So you accumulate the votes, the partial votes, which would be interesting to have an election with partial votes. Actually, it's not a bad idea. It's an interesting idea. You allocate your votes to the candidates proportionately to how much you like them, how much you want them to win. And then you sum over all the voters or experts or hypotheses, and then you check which label got the highest cumulative vote. This is the Bayes optimal classifier. And it is optimal in the sense that its probability of error is the lowest of any possible classifier given the same, given the prior and the likelihood are correct. The problem is, we said, so this is optimal. There's a good reason it's called optimal. The problem is, of course, computational. What if the number of hypotheses is very large or infinite? What do you do when you try to vote? You want to sample every doctor. You want to consult every doctor in the country. Okay? Every cardiologist in the country, but there are 40,000 of them, and you can't reach them all. You still want to make a decision between 3 possible surgeries. What can you do?
Take a random sample.
I'm sorry?
Take a random sample.
Take a random sample. Yep, you can do that. If you have a large number of experts or a large number of hypotheses, ideally you want to know which of the 3 possible recommendations would get the most vote, but you cannot consult all 40,000 of them, so you take a random sample of maybe 50 or 100 of them. You can do the same thing with hypotheses. The only thing you have to be careful about is if the doctors vote according to their seniority, let's say, how many years they've been a cardiologist. A doctor who's a cardiologist for 40 years get 40 times more vote than someone who's been a cardiologist for 1 year. Okay? Now if you're going to scan all 40,000 doctors, cardiologists in the country, that's fine. But if you're going to sample, you have to make sure that a doctor that has been practicing for 40 years has a 40 times higher chance of being selected than one that was only practicing for 1 year. In other words, you want them to be selected for your sample proportionately to the vote they have. Otherwise, it will not be a representative sample of what the outcome would be. You can think about it as each doctor is given 40 votes, or as many votes as they have been practicing, and they are given little ribbons. So one doctor gets 40 ribbons, another doctor gets 5 ribbons, another one gets 1, and they put them down on the table, and there's a total of 200,000 ribbons, and then you sample randomly from the ribbons, not from the doctors. Such that doctors that had more ribbons are more likely to be chosen. That's one way to think about it. But nonetheless, going back to the hypothesis, you want to sample from the hypothesis, but you want to sample proportionately to how likely these hypotheses are, namely proportionally to the posterior. How does one do that? Well, remember the posterior is add to 1. So if you take your first hypothesis, this is 1, from 0 to 1. The first hypothesis, H1, has a certain posterior probability. It's right here. This is H1. H2 might have a larger posterior, let's say up to here. H3 might have a tiny posterior, and H4 might have tiny too. And you can put the slices here. You can even have 1,000,000 of them or more. And the total area must sum to 1. And now if you draw a number randomly and uniformly in the range 0 to 1, that will place you someplace here, corresponding to a particular hypothesis Hj, and it will do exactly what we wanted to do, namely, the larger the area of Hj, the more years that doctor has been practicing, the more likely the point is to fall in their area. So if you're in a situation where you can do that, where you can list the posterior explicitly, let's say you only have 1,000 or 1,000,000 or even 1,000,000,000 hypotheses, you can do that without a problem, and you can sample this way and collect the opinions of the hypothesis you sampled and stop after a modest number, 100, and then the answer you get is going to very likely be the same answer you would get if you systematically went over all of them. Now you may be in a situation where the number of hypotheses is not finite, is infinite, could even be uncountable, could be a continuous space. And then the question is, are there ways to sample from a continuous space proportionately to the posterior? And that all depends on the shape of the posterior, the shape of the posterior function. Some posterior functions are easy to sample from, other functions are very difficult to sample from. And you'd be amazed that there are thousands of papers on how to sample from certain functions, used not only for the Bayes optimal classifier, for other things too, but this problem of sampling from a function comes all the time. And sometimes you can't do it exactly, but you can sample from a similar function that is easier to sample from. So you can start making corrections. How big of a sample would you take, if you could? You want to suggest a number? One? Yes, no? 100? What's better, to sample 1 or to sample 100? 100. What's better, 100 or 200, ignoring cost? Right, the larger the sample, the better. Right? If you ignore cost. Suddenly, if you sample just 1, that sounds a little strange. It reminds me of a science fiction story I read a long time ago. I think it's Asimov, I'm not sure. I'm pretty sure it's Asimov. Where election science was so accurate that people could predict who, you know how Ohio is considered the center of America, and that there are certain cities in the US that are considered exactly representative of the middle of America, not too conservative, not too liberal, and so forth. Well, it got down to such a ridiculous extreme that the computers could choose one person, and that person would vote who would be president. And the result would be identical to what it would have been if you let everybody vote. That's Asimov, that's not me. But anyway, that was the assumption. And the big issue is who the computer is going to choose. And the computer was looking at the demographics of everybody who's going to choose that one person, is going to save them a tremendous amount of money because you don't have to go through an election process. Or maybe you just direct all of your propaganda at that one poor person. And then they choose, and then you know that it's the same. Okay, in the real world we don't know that it's the same. But you can imagine just choosing one hypothesis based on the posterior, just drawing one dart into this line and taking the outcome of that dart. Now that seems pretty stupid. A sample of 1 is extremely unreliable, right? And in general, you would be right. But interestingly, under some conditions, doing that is not much worse than doing the full optimal Bayes, like summarizing of the whole thing. Specifically, the error rate of just shooting one dart and taking whatever answer is no worse than twice the error rate of the optimal Bayes classifier, the one that you get by asking everybody here. Now that sounds very counterintuitive. How can it be no worse than twice the error? So it is worse. It's not the same, but it's no worse than twice the error. To try to give you some intuition for that, no worse than twice is not necessarily a good bargain. If the classifier to start with is not great, then the error rate, let's say, I'm sorry, I'm talking about cases of binary classification. Actually, no, it could be any kind of multi-way classification, but let's think about binary classification. If you have a random classification, you have a 50% error. And being twice as bad as a 50% error is a 100% error. So that's not a great bargain. But more likely, we're talking about cases where the classifier is not bad, the posterior is a pretty good posterior, and the error rate is maybe 2%. So if you went over and summed the contributions of all your hypotheses proportionately to their posterior, or if you had to integrate it, and you did a lot of work, and at the end you get the classification that the Bayes optimal classifier gives you, you have a 2% chance of still being wrong, on average. If instead you took a dart, threw it at that line, and wherever it landed you chose that hypothesis, and you consulted it, your average error would be 4%. So that's pretty good. Question? What is the exact time for the average error? So, assume that the data, that the world really behaves according to the prior. So every day when you wake up, the prior is consulted and chooses the value of the parameters. And then from the parameters, the likelihood function is consulted, and it chooses the data. In the case of classification, let's say you have two. I'll give you a simple example. Let's suppose the data came from two Gaussians. You have a positive and a negative. You're trying to classify into plus or minus. The plus points came from this Gaussian. The minus points came from this Gaussian. I don't mean to make this taller than this. They're both the area for each one of them is 1. One of them could be higher than the other depending on how wide they are. But let's even assume that they have the same standard deviation. So this is mean plus, and this is mean minus. And the standard deviation is known to be 1, so we don't have to worry about it. Now you're given a lot of data in the form of x values and whether they are pluses or minuses. So you'd get a lot of pluses here, especially they'll be concentrated around the mean here, and a few here, and you'll get some minuses here. Now you don't know where the means really are. All you're given is a bunch of x's and whether they are plus or minus. And maybe you're told that they came from two Gaussians that each have a standard deviation of 1, and you ask to find the means. So the parameters of the system are the means. Theta consists of mean of the plus part and mean of the minus part. Now you may have some prior over the means. Okay, that's important. In the Bayesian setting you have to have a prior over the means, some story of how they were generated. And then you have a likelihood function, which given whether you're in a positive case or a negative case gives you the likelihood of the data point. And then you can write your Bayes classifier. Maybe we should do that. Let's do that now. It'll set us back a little bit, but I think it's a nice thing to do. So here's our setting. You have a prior over the two means. You have to decide how these means were generated. Maybe they themselves came from Gaussians, hyper-Gaussians. Maybe they're drawn uniformly between 0 and 1. There could be anything. Then you have the likelihood function. Likelihood of each particular item xi and I should add to the prior, there's also the prior probability that you would be in positive class or in a negative class. Okay? I don't know what to call that. Let's call that theta, as in probability of head. P of plus. Okay? The likelihood, which of course depends on the parameters, or in other words, the likelihood of xi depends on mu plus, mu minus, and p of plus. I'm already only writing p of plus here because p of minus is 1 minus p of plus. Okay? Now I'm going to write it. How likely am I to generate this theta xi? Well, I could have generated it as a positive point, or I could have generated it as a negative point. Right? So there's a probability of p plus that I generated as a positive point, times there's a probability of generating this xi given that I'm in a positive case and I'm using mean m plus the probability minus p minus, which is 1 minus p plus, times the probability of generating the same data point given that I'm in the minus case and mu minus. I only wrote here mu plus because mu minus is not relevant here anymore, and the same here. So I'm able to write down the likelihood function, which it also always depends on the data given the relevant parameters. Now I can, given a lot of data, x1 through xn, I can use Bayes' rule in principle to generate a posterior. The posterior would be a distribution over the three parameters of I'll write it higher. The posterior would be a distribution over the three parameters of interest to me, conditioned on having seen the data. So remember that I have a prior. This is the prior over mu plus, mu minus, and p plus, and it goes into the Bayes machine, as does the data, and out comes the posterior, which has the same form as the prior, except it's conditioned on the data. So it's the probability of mu plus, mu minus, and p plus conditioned on the data. Now I'm finally getting to your question. Now I did everything that Bayes wants me to do. I arrived at the posterior. Now how do I use that posterior? I'm given a new item, and I'm trying to classify it. New item x, I don't know, n plus 1. And I'm trying to classify it as a plus or minus. My hypothesis space is now continuous. Not only is it continuous, it's also three-dimensional. So to consult all of my hypotheses, I will need to integrate 3 times. 3 nested integrals. I'll need to integrate over all possible values of p plus, all possible values of mu plus, and all possible values of mu minus. Now I'm running my election. Okay, or my referendum rather. First I'll give him the weight. The weight that each hypothesis should have is the posterior, p of this particular mu plus, mu minus, p plus, given the data. This is the weight it has. And now I'm going to give it how much that particular hypothesis votes for each one of the 2 outcomes. That is basically the likelihood of these outcomes under the assumption of these particular parameters. But it's not the likelihood of the data, it's the likelihood of my new item. So this is the p of xn plus 1 given my parameters mu plus, mu minus, and p plus. And now I have to finish the integration, dp plus, d mu plus, d mu minus. I'm sorry, I missed this. This is how much it votes for the plus option given xn minus 1, xn plus 1. So I'm given the xn plus 1, I'm giving the value of the tentative value of the parameters, namely which hypothesis I'm in right now. How much do I vote for p plus? For the plus outcome. I apologize. And I have to repeat that for the negative outcome, but we all know it will be 1 minus this. And now, if instead of calling it plus, I'll call it Zi, where Zi is plus or minus. So Z1 is plus and Z2 is minus. My 2 labels. Now I can write here argmax over the Zi's. Zi goes from plus or minus of this expression. This is what a Bayesian would do. This is a typical story of what a Bayesian would do. They would write a posterior, they would integrate over the posterior times the likelihood of the item, of the label, of the new item, and basically do the elections this way, and then try it for all possible labels and choose the one that is highest. This is not the maximum posterior hypothesis. Okay? This is the Bayes classification. Now let me finally answer your question. What kind of error are you going to have there? And the answer is, even if you do this right, if you do all of this, you're guaranteed to have the lowest possible average error over, when you asked about what kind of average, the answer is average over lots of data that comes from this kind of process. Namely, if the data really came, if the way you got the new data is indeed by sampling from this, the way you got your training data is by first sampling from this, then fixing these values, then generating the data, and then generating the n plus 1 item, the probability of error would be lowest if you went through this process. That error would correspond to the area here. this overlap between the two Gaussians, it actually, theoretically, it goes on forever, right? Because the Gaussian never get to 0. But it's mostly, to a good approximation, it's this area that you can see as overlap. In the area of overlap, your error is going to be about half. Not exactly right. I mean, it's going to be half when it's right in the middle. If you have a point that's right in the middle between the two Gaussians, each one is equally likely, assuming an equal prior. And then if you just choose one of them, you have a 50% chance of being wrong. If you're more to this side, then you're better off choosing this Gaussian, and you're less than 50% chance of being wrong. And the same in the other direction. But very roughly, intuitively, the error that you have, it's called the Bayes error, and it's an error you cannot avoid. The Bayes error has to do with the intrinsic overlap between your classes. It's something that you cannot avoid, that there's no data anywhere that will save you from it. It comes from the fact that the same data point could have been generated by the two different labels. And even if you know exactly with what probability, so it has to do with, for example, if you knew for sure the probability of head is 0.8, and every time I flipped a coin, what would you guess to minimize your error? You would guess head all the time, right? But 20% of the time you will be wrong. It doesn't mean you use the wrong procedure, you use an optimal procedure, you cannot do better than that. But you still be wrong. That would also be called the Bayes error. It's unavoidable error. It's the error you get if you use the best possible prediction, if you had complete knowledge of the situation, as we assume here. Did that answer your question? It was a very long answer, but... Any other questions? So the method of throwing a single dart at the space of hypothesis and choosing one hypothesis and using it is called Gibbs sampling. And it's very counterintuitive that its error is only twice the error of a full optimal Bayes classifier. But it's true, and I think the proof is in the book. If it's not, think about it. It's a nice thing to prove, and it's not too difficult. We're a little bit behind. On Thursday, we're going to have to catch up and discuss both naive Bayes and Bayes nets. All right, thank you.